Hello everyone, and welcome back to my YouTube channel. My name is Ernest Jha, branch CSECY, USN 1VE23CY001 for second SEM section gapping. The subject today is mathematics and the topic is analysis of probabilistic models. Introduction to probabilistic models. Probabilistic models are powerful tools for understanding and making decisions in the face of uncertainty. These models use probability distributions to represent and quantify the likelihood of different outcomes, allowing us to reason about complex systems and make informed predictions. Probabilistic models. Probabilistic models play a pivotal role in machine learning, allowing us to handle uncertainty and make informed predictions. Let's explore them further. What are probabilistic models? Probabilistic models are statistical tools used in machine learning to capture the inherent uncertainty present in data. Unlike deterministic models that provide a single outcome, probabilistic models consider multiple possible outcomes, accounting for randomness and variability. These models are essential for various applications, including image recognition, natural language processing, and recommendation systems. Naive Bayes algorithm. A classic example of a probabilistic model is the naive Bayes algorithm. It leverages Bayes' theorem and simplifying assumptions such as feature independence to calculate the probability of a target class given a set of features. Despite its simplicity, naive Bayes has proven effective in various real-world problems, from spam filters to medical diagnosis. Categories of probabilistic models. Generative models. These models aim to capture the joint distribution of input and output variables. They can generate new data points based on probability distribution learned from the original dataset. Useful for tasks like image synthesis, language translation, and text generation. Discriminative models. These models focus on modeling the conditional distribution of the output variable given the input. They learn decision boundaries to separate different classes, commonly used for tasks like image recognition, speech recognition, and sentiment analysis. Graphical models. Graphical models represent the conditional dependencies between variables using graphs. Widely used in image recognition, natural language processing, and casual inference. In summary, probabilistic models allows us to navigate uncertainty, make accurate predictions, and understand complex systems. They are the backbone of modern machine learning, shaping our ability to learn from data and anticipate future outcomes. Probability distributions. Discrete distributions. Probabilistic models often rely on discrete probability distribution, such as Bernoulli, binomial, and Poisson distributions, to represent the likelihood of events with a finite number of possible outcomes. Continuous distributions. Continuous probability distributions, including the normal, exponential, and gamma distributions, are used to model quantities that can take on any value within a range, such as measurement data or physical quantities. Multivariate distributions. In many real-world scenarios, multi-random variables are interdependent. Multivariate probability distributions like the multinomial and direct fit distributions can capture these complex relationships. Bayes theorem. Conditional probability. Bayes theorem provides a way to update our beliefs about the probability of an event given new information or evidence, prior and posterior probabilities. Bayes theorem allows us to calculate the posterior probability of an event, which incorporates both the prior probability and the likelihood of the new evidence. Applications. Bayes' theorem has numerous applications from medical diagnosis to spam filtering, where it is used to make inferences and decisions based on incomplete or noisy data. Markov chains states. Markov chain models system that can be one of a finite number of states and where the probability of transitioning to a new state depends only on the current state. Transitions. The transitions between states in a Markov chain are described to be a transition probability matrix, which encodes the livelihood of moving from one state to another. Equilibrium. Markov chains can reach a steady state equilibrium distribution, where the probability of being in each state stabilizes over time, regardless of the starting state. Bayesian inference. Introduction. Prior distribution assigning probabilities to possible values before observing any data. Likelihood function, assessing the probability of observing the data given different parametric values. Posterior distribution, updating the prior probabilities based on the data to obtain the posterior distribution. Decision trees. Decision trees are a popular machine learning algorithm used for classification and regression tasks. They provide an intuitive visual representation of the decision-making process, making them easy to interrupt and explain. Decision trees learn from data by recursively splitting the input space between on different features, ultimately leading to prediction or decision outcomes. Hidden Markov models. Unobserved state. Hidden Markov models are a generalization of Markov chains where the underlying states of the system are not directly observed but must be inferred from the observed sequence of outputs. Parameter estimation. Hidden Markov models have parameters that describe the transition probabilities between states and the emission probabilities of the observed outputs. These parameters can be learned from data using techniques like the expectation maximization algorithm. Applications. Hidden Markov models have been successfully applied in a wide range of domains, including speech recognition, bioinformatics, and finance, where the underlying processes are not directly observable. Inference. Powerful algorithms like the forward-backward algorithm and the Viterbi algorithm allow us to perform inference in hidden Markov models and find the most likely sequence of hidden states given the observed data. Gaussian process. Non-parametric. Gaussian processes are a powerful non-parametric approach to modeling functions where the goal is to learn the function directly from data without making strong assumptions about its form. Covariance. Gaussian processes model the function as a distribution over functions where the covariance function encodes our assumptions about the smoothness and structure of the underlying function. Uncertainty. Gaussian processes provide not only a point estimate of the function, but also a quantification of the uncertainty in estimate, which is useful for tasks like active learning and decision making under uncertainty. Application. Gaussian processes have applications in a variety of domains, including regression, classification, optimization, and reinforcement learning, where flexible and uncertainty aware modeling is crucial. Monte Carlo methods, sampling. Monte Carlo methods rely on repeated random sampling to approximate complex mathematical expressions or integrals that are difficult or impossible to solve analytically. Simulation. By simulating a large number of random samples, Monte Carlo methods can provide estimates of quantities like expected values, probability distribution, and uncertainty intervals. Application. Monte Carlo methods have a wide range of applications from pricing financial derivatives to simulating complex physical systems and optimizing complicated functions. Application and limitations. Applications. Predictive modeling and forecasting, decision making under uncertainty, risk analysis and management, simulation of complex systems, optimization and inference problems. Limitations. Reliance on accurate probability models, computational complexity for large scale problems, sensitivity to model assumptions and parameters, difficulty in interpreting and communicating results, potential for bias or misleading conclusions. Thank you. Thank you for watching my video. I hope you found it informative and subscribe and like.